about our reflections. Now, reflections are one of those things where you can just memorize, hey, if I reflect over the y, I make the x negative. If I reflect over the x, I make the y negative. But the visual is really helpful too. You know, it's one of those things, if you forget it, you just make a quick sketch and say, all right, there's xy. If I reflect that over the x-axis, now it's going to be x negative y, and that will make total sense. You know, that, yes, that's what it was. It's the opposite one that gets the negative, you know. So if you just make yourself a quick visual, you're taking the ACT, you're taking the MCAs, you forget, it doesn't take long for you to get it. And then if you have your XY and you reflect over the Y-axis, of course the X becomes negative. So this was right below example 2 in your notes. I didn't uncover these boxes yesterday because I kind of wanted to start with that today. So keep in mind, reflect across the X-axis, make the Y negative. Reflect across the Y-axis, make the X negative. Because that's going to be really important when we start talking about transformations of things you haven't necessarily done a lot of transformations with before. Alrighty, away we go. We've got reflecting even functions, which we had talked about. Let's see, where did we finish? We did the absolute value stuff. That was cool stuff. I like that. That's cool stuff. So, that was done. That was done. Did the little proof. Did the absolute value. Ran out of time. Yeah, that's where we were. So right here, it says identify the parent function and the transformation in order. You have to remember parent functions are the most basic function of any type that we have. For instance, if you want the parent function of an absolute value function, it's y equals the absolute value of x. Because that's all you need to make something an absolute value function is absolute value of x. If it's a square, a parabola, well, that's quadratic. So the parent for that is just going to be y equals x squared. So you can use the powers when we're talking about quadratics, cubics, quartics, etc. That's a good idea. So now, think, am I supposed to remember what's going on there? Well, yeah, because this is vertex form. And with vertex form, we always did the A, H, and K thing. Thank you. With the vertex form. And we know we're supposed to follow the order of operations, but that becomes very incredibly important in pre-calculus. You know, in Algebra 2, we would say, well, technically, if you did these in this order, they'll still give you the same transformation, so we'll give you the points. We're not going to do that in pre-calculus because that is absolutely not true in pre-calculus. You have to follow the order of operations. So this little bugger here would be what we deal with first because those are parentheses. And we have to remember it's the opposite of whatever we usually think. So this x minus 3 is actually translate 3 units to the right. Because h itself was a 3. And then that negative 5 in the back is translate 5 units down. So you follow the order of operations. You say, I got to go inside the parentheses first. Anything that's being multiplied will be next, and then add and subtract. So this little bunny right here looks like so. What do we say first about that? Translate 3 units left. We got to say the reflection now. Again, the order is really important. Normally you do parentheses, do the squaring, then the negative. So reflect over the x-axis. What's last? Translate 4 up. Four units up. Then we get to y. For y for c. Y equals the square root of x plus 3 minus 1. And I think, okay, Parent of this bugger. Notice I didn't write the parent down on the last one because it was the same parent function, y equals x squared. This one is the square root of x. There's our parent function. And with these, I can't remember if we had to write that down on the test or not. We maybe did because on the test we're not doing them all. You know, we're not going to have you do all the quadratic, all the cubics. We're just going to pick one or two and put it in there. So this one, our parent is y equals the square root of x, but we still have our h and k business. So what are the transformations for this one? Then we get to D, and there's a problem. Does D fit our form? No. We like our form. Our form is so nice. We're going to make it fit. But to make it fit, we have to do something different. So what we'll do is this. We'll say, you know what? That x has to be first, and it has to be positive. So I'm going to have to pull a negative 1 out of this. Like so. Now, this will work like normal, except for one thing. What's the one thing up there that's messing it all up? We have to take that out of the picture immediately. We have to. Otherwise, all of what we know will not work when we transform this. So I think, what was that negative really doing? It was making my x negative. What makes your x negative? Oh, that was a reflection over the y-axis. Now it's back to normal because now it's gone. We've taken it out of the equation. You know, we've described what happened there. So after our reflection over the y-axis, we can just say, here are the translations. So what's the translation we deal with first? Careful. Translate. Next up. Cannot stress how very important it is to get that negative 1 out of the picture before we do our normal stuff. This does not fit our A, H, and K unless that is gone. You have to deal with that first. Otherwise, our form is useless when we go through this. And actually, if you do the transformations visually, like you just take a segment and you do all of these transformations, you're going to see it makes a big difference. So you can't just arbitrarily decide what to do first. Make it fit the form, then follow the order of operations. So down here it says, let's make some stuff happen to our parent functions. Write an equation for the transformations of the given parent. And A says we're going to move that little puppy right 6. So what do? If it's to the right, does it have to be inside the absolute value bars or not? It has to be. How do we make it go right? Good. Exactly. Reflect over the y-axis. What do we have to do to reflect over the y-axis? That's it. And just the x, everybody. Just the x. How do we get it up 1? Slap +1 in the back. We've made it happen. All right, the next one says we have this little y equals 1 over x business. We're supposed to reflect it over the x-axis, so what do? We sure do. Bless you. And then we know we're going to have to divide by a -1 or multiply by a -1, because that's just what we do. Then what? Round 5. And there it is. So transformations. Normally, it just works according to what we do in Algebra 2, but there's some new stuff here. So let's look at C. Parent is the cubic function. How do we reflect it over the x-axis? How are we going to make that move to the left? Yeah, it has to be in parentheses. And what do we put in those parentheses? Good. Don't forget your little cubic. You know, that's something we do because we get going too fast, you know. Y equals e to the x, Euler's number. Left 3. Oh, how are we going to do that? It's going to be a part of the power. Yeah, it has to go with x. We know that. Any movements in the horizontal direction go with x. So x and what? Plus 3. Reflect over the y-axis. Put a negative in front of the x and just the x. Got it. Got it. So lots of different parent functions we were looking at there. Now, we're going to learn something brand new in a minute. And that is this.
Just like, so, like the other equation, like y equals x greater than y equals a equals x minus h, like that, what would that equation be? Y equals
That was in your book. Y equals a times e to the x minus h plus k. Yeah, a little awkward.
That's what it could be.
Yeah. No, it's a little awkward, you know, but it does what we need to do. Horizontal staying with the x as you go through that. So on this page, they have this whole graphing thing, which would be wonderful if we had 3 days for this section, but we don't. So I'm going to give you the short and sweet version. When we graph, and we have numbers that we are multiplying our functions by out in front, those are vertical transformations. And we know that if that number that we're multiplying by in the front is a number bigger than 1, that we have a vertical stretch. So this would be a stretch because 1.5 is bigger than 1. This would be a stretch. And then when we multiply by fractions between 0 and 1, those are called compressions. And now, last year, you know, your teacher may not have been incredibly picky about you saying vertical stretch, vertical compression, because that's all you study in Algebra 2. We also study the horizontal stretches and compressions in pre-calculus. So these, I think, you know what, x's and y's always work the opposites of each other, you know? When you deal with k in the back, a plus takes you up and a minus takes you down. But when you deal with x in the middle, it looks like a minus something when you're actually moving it to the right, and it looks like a plus something when you're actually moving it to the left. So for vertical stretches, I multiply by a number bigger than 1. X's must work the opposite of that, because that's just how they work. And that is, in fact, how horizontal stretches and compressions work. So I see this as my A factor inside that square root piece. And I think to myself, how did that get there? You know, if they've got the square root of 4 minus 1.5x, all of that squared, what really happened there? Well, to get it to multiply by 1.5, they really divided by 2/3. Because when you divide by the fraction, you're going to be multiplying by the reciprocal. So now we have to think opposite. If we see 1.5, which looks like, hey, that's a number bigger than 1, that should be a stretch. That was actually a compression. This is a horizontal compression. Sorry? Got it? Okay. So we're looking at this and it looks completely different, than you've ever done before because you've never taught horizontal compressions before. And these are your accordion compressions. Here, take an accordion. You guys even know what an accordion is. Have you ever seen an accordion? Okay, really bad polka music. Yeah, in and out. So our horizontal compressions are squishing that graph horizontally, and then the stretches are pulling that back out. So this one is a horizontal compression factor of what? What did they divide by to get that 2 there? 1/2. They divided it by 1/2. What we know about the vertical is the opposite with the horizontal. So this one, even though in our mind we'd say, oh, that's got to be a compression, that's not a compression. How did they get that 1/2 in front of it? They divided by 2, which would be a stretch. So this is our, oh, we have passed it. Okay. So this one would be a horizontal. Stretch. Factor of 2. Because when we divide by 2, we're really multiplying by 1/2. Bam. Yeah, yep.
Why is it division multiplication? Why is it division opposite?
There are so many patterns that have just been studied for hundreds of years, Kevin. And so, somebody realized when I want the vertical to happen, it's always multiplication. And just thought, okay, since the x's work so backwards, it must be division. That must be what makes it happen. And they discovered it, Since math has been around for so long, there's always somebody that says, hey, you know what? I never noticed this before. Now I see it, So what was our vertical stretch factor if it's 1/4 in front of there? A 4. Yep. So you have to kind of think backwards about the horizontal than you do from the vertical.
So when they say shrink, you say compression,
Yes.
They call them shrinks.
And most books go with compression. Yeah, I'm sure this book went with shrink. And that's because the AP exams, they want to see the fancy language. They want to see compression versus shrink. They don't want you to say shift 3 units up. They want you to say translate 3 units up. Yeah. Oh, I remember that when I checked my answers for that last homework assignment. Yeah. Wherever they say shrink, it should be compression. Did they use stretch? Do you remember, Cassie? I don't remember.
Yeah, they did.
Okay, stretch was good, but they really should be using compression whenever they talk about the word shrink. Should be compression. All right, stretches and shrinks. Let C be a positive real number, then the following transformations result in stretches or shrinks of the graph y equals f of x. So y equals f of x of c. This is what we're talking about. The x is affected by this number. So it's actually the opposite of what we would normally think. And down here, we see the verticals. So again, this is the division piece, and we just have to think backwards about what we know. So just, here's my vertical, I remember all that stuff. Now think backwards about my horizontal. Example 5 says, finding equations. Get it back up there. Finding equations for stretches and shrinks. Let C sub 1 be the curve defined by y sub 1 equals f of x, which equals x cubed minus 16x. Find equations for the following non-rigid transformations of C sub 1. So non-rigid means the shape is changing. That's what it means. And it says C sub 2 is a vertical stretch of C sub 1 by a factor of 3. Well, that's old stuff. Vertical stretch means we're going to multiply. So we'd have to take x cubed minus 16x, and we'd have to multiply that by that factor, which is 3. And they want us to call that C sub 2. All right, so that one it's normal, you know, it's what we would normally think of because it's the vertical piece. And then this one says C sub 3 is a horizontal shrink of C sub 1 by a factor of 1/2. Okay, so to get C sub 3, we're going to have to take our function, whatever it is that has the x's in it, and we're going to have to divide that by 1/2? Not really, right? So what does that do? It multiplies by 2. So really, we just need to multiply our x's by 2. So wherever we see the x's up here, we're going to have to deal with 2x. And notice with the x's, we have to put it in both spots. You know, this wasn't vertical, which deals with the y's. This was the x's, and that means we have to replace them. So this is going to be 8x cubed minus 32x. And never a bad plan, especially as we get used to this whole, you know, horizontal business, to go ahead and graph it and see that that's happening.
Why did you put that 2x minus 16?
Because this one is about your horizontal shift, and your horizontal shift is about your x's. So what we have to do is make sure that in every x position, we are shrinking it by a factor of 1/2. And that means both of them are going to get the 2x. So everywhere you see it, that's going to happen. We had the nice easy one last year in vertical. Horizontal takes a little more work. You know, it really does, a lot more thinking. So there is our vertical stretch, which, like I said, you covered that last year. You know, all you do is you take all of those points, and it's like you have a rubber band for your function, and you stretch it up and down. But this little bugger is saying we've got our original, and then we're going to squish that by a factor of 1/2 horizontally, and we can see that. So the numbers all tell us something, and we need to pay attention to those numbers. So on the next page, putting it all together. Now that we have more and more stuff to do, this says we're going to combine those transformations, and we're going to make sure that we have this in order because the order does matter. You will get 2 different graphs if you don't do the order exactly like it says to do. So the graph of y equals x squared undergoes the following transformations in order. Find the equation that graphs the results. So we're starting with this. And we need a horizontal shift 2 units to the right. How are we going to do that? Everybody okay with the x minus 2? Good, nobody forgot that part? All right. So a vertical stretch by a factor of 3. Where's it go? Exactly, right out front. The easy way from last year. You know, it's A. It's out in front. Vertical translation 5 units up. How about if we did it backwards? That's the question. Will we get the same thing if we do this backwards? So if we want to compare this, we really should put this in standard form, so we'll see the difference. and that means we should actually do the multiplication. And see what happens to the whole graph by going the opposite direction. So y equals 3 times x squared minus 4x plus 4, and all of that plus 5. That would give us 3x squared minus 12x plus 12 plus 5. So 3x squared minus 12x plus 17. Now, if the second one that we do doesn't give us the same thing, we know order matters. It does. So we're going to put them in the opposite order this time. Vertical translation 5 units up. What do we do? Add 5. Vertical stretch factor of 3. What do we do? Put 3 out there. What's next? Yeah, we need this horizontal shift 2 to the right. Almost immediately you can see we're not going to get the same thing. We're just not. Because now we do all this math first, and then we multiply by 3. And oh, we're not doing too bad, are we? 33? All right, so let's go ahead and do the math on this one. X minus 2, the quantity squared. And then our 4 and our 5 are like terms. And we distribute. It's close. What's different? Yeah, that last number out there, that's the y-intercept. That's the y-intercept. So our y-intercept was at 17 before. Now it's at 27. Well, everything else is, the shape of the graph is the same, but this has a shift in it. So we can see, yeah, the order matters. You know, you can't just decide I'm going to do this part first and this one second. So we have to follow that order of operations as we go through. And we try to use our A, H, and K formulas as much as possible. Every once in a while, that means we have to deal with taking a negative out of there first in order to get it into the form that we use. The graph of y equals f of x is shown in figure 1.78. Oh, isn't that great? Look at that little bugger. We don't even get an equation on that. Determine the graph of the composite function y equals 2 times the function of x plus 1 minus 3 by showing the effect of a sequence of transformations on that graph. So they're not giving us the equation, they're saying this is the original parent function with this stuff happening to it. And we know the order of operations is important, so we deal with this first. So where's this graph going to go? Which way in here? Left 1. All right, well, we'll do the best we can and move some of these points left 1. Anything that looks like a critical point. And this needs to be dashed, and that's because this is not my final graph. It's one of the steps in 3 steps here. All right, so that's 1 to the left. What's next? Yeah, we have to go out front. You did the parentheses, now you go out front. Vertical stretch of 2, how are you supposed to do that if you don't have the equation? Well, you stretch all the y's 2. So, this isn't going to go anywhere because the y's right here are 0. But we could kind of use this one at 2 and say, hey, if I have to double that, that's now going to be 4. That's a little off. I can even tell standing on the side here that that's a little off. I think I graphed a little bit too far to the left. So it looks like we grabbed the top of it and we pulled. One more to go. It's the last one, last translation. Down 3. So let's take our 3 critical points and just move those y's down. 1, 2, 3. 1, 2, 3. 1, 2, 3. Would not turn out the same way if we had just indiscriminately picked how we're going to do this. We follow those order of operations and use our AH&K information as much as we possibly can. In this case, without a formula, it gets a little challenging. You know, it's a matter of, boy, how am I going to draw this? Well, look for those critical points. That's what we need to do. To summarize, when sketching a new graph by a sequence of successive transformation, multiplication must be done before addition, subtraction. Not always, you know. The multiplication piece they're talking about is the goofy one that happened for us inside the square root. We had that -1 piece. We had to get that out of there. We had to do that. So this is not a in stone thing here. Inside changes are the opposite of what they immediately appear to be. That's kind of an oversimplification of the fact that horizontal changes are always backwards from what we expect. Mathematically, with the numbers, that always happens. That x horizontal piece is always the opposite. And then outside changes, those are exactly what we would expect. Now, they didn't just put this middle bullet in here just because of the h. It's also because of our vertical compressions and stretches. Whatever's in the parentheses, whatever's in the brackets, whatever's in the absolute value bars, you have to think opposite of everything that you know about the stuff that's outside, because the x's work that way. The horizontal movements are always the opposite of what we think. All right, so we've got you try. Determine the parent function and the transformation. Sketch a graph without using a calculator. Find a few key points such as f of 0. State the domain and range using interval notation. Oh, let's see. Let's do this one. That one's a line. Yeah, I guess we haven't really ever talked about lines in this way, so let's get y by itself and let's talk about this one. All right, so there is the graph. And we don't do a lot of parent function stuff with lines, but our parent function is always that perfect diagonal through first and third quadrant line, which is just y equals x. Now, if I follow the order of operations to talk about the transformations of this line, I'd have to do this multiplication piece first. This -2/5 is my a. So what is this -2/5 telling me? That's my a value. What does it say to me? Vertical what? Compression. Don't let the new stuff we did mess with your head. We've got a vertical compression factor of 2/5. What does the negative tell me? So then what's the +3 for in the back? Of 3. So the parent function, perfect diagonal through first and third quadrant. And I was watching some of you, you were already graphing this line. But I want you to think of it in a new way. You know, think about those transformations that took place. We go up here to 3, and then we use our slope to get a second point, so down 2 and to the right 5. If you took that line and you squished it, you're a giant, and you squish this line by 2/5. You can see how that slope has changed because of that. And we definitely see that flip, and then it's moved up 3 units. It's just a different way of looking at something that we already knew how to do. That one's pretty basic. Tell me the transformations for B, please. What are they, or we'll do the whole thing? Left 3. Down 1. You don't need that one. That's A, H, and K all the way. It's got A, H, and K written all over it. I would love to have A, H, and K in C, but I don't. How can I get A, H, and K? Factor and or complete the square. Complete the square. Well, Cedarholm, to complete the square, you have to have a 1 in front of x squared. Why, you're absolutely right, you do. So we need to get rid of that negative. Let's divide everything by -1. What's our next move to complete the square? Yeah, that -3, that is not helping us at all. That is not what we need to complete the square. What do we need? That's a little formula. B over 2 squared. What do we need? 1. -2 divided by 2 is -1. Square it, and you get a 1. So how do we write that perfect square trinomial? Already looking much better, but now we need to get y by itself. Subtract 4 and divide by a -1. Yep, yes, you got it. Oh, fine, move up. There we go. And I don't know about you, but I'm pretty confident you guys could describe those transformations now, right? Wouldn't be an issue at all. No, okay. Oh my goodness. What in the wide world of sports is that? That, my friends, is a circle. So Cedarholm, how did you know that was a circle? Because circles have x squared plus y squared equals r squared. X squared plus y squared equals r squared. And that's what happens when you move the horizontal coordinate. That's what happens when you move vertical. Because you have a new vertex. You have a new vertex. The normal vertex for a circle that would just be x squared plus y squared equals r squared is 0, 0. But this one has moved it. That's what's happening. So with our circle here, we have to think, so what happened from this to that? Which way did they go? How do you know it's down 5? Which is it, everybody?
It's up 5.
It is, it's up 5. So some of the things that we know about our normal x minus h, stuff and y minus k stuff, you look at that, oh, wait a minute, that's not up 5. You guys just convinced me of that. Take a look at the formulas. Yeah, it's down 5. Always the opposite. Always the opposite. So even though it's a y, which I know that's how they baited you into that. This formula for circles is a little bit different because both the x and the y get the minus in them. So they baited you. Now, how are we going to draw this? We need to find a new vertex. Well, this doesn't have a new spot, so that's going to be 0. And I guess we call it the center, not necessarily a vertex. And then -5.
So the reason for shift is translate.
I should put translate. Thank you, Emmy. I will accept, on the test, we accept shift. But like I said before, when you take the AP exams, really should do the whole translate business. Compression versus shrink, all that good stuff. So you're right, if I'm going to model it right, I should write translate. So there's our new center at 0, -5. 1, 2, 3, 4, 5. It's a circle. I suppose I should know what the radius is because then I can draw. 2? How do you know it's 2? Because r squared was 4. So we're going to go 2 out in every direction. And then we do our best to draw something that looks round. It's a little easier when the big circles are really tough to do. There it is. Now where are some other ones that I absolutely wanted to go through with you? The very next one. What, was there anything else we were supposed to tell them on this? Oh, domain and range. I'm not sure we need to do that together. You guys feel okay about domain and range? Okay. Well, then let's do it with the circle. That would be a good one to do that domain and range stuff. Domain of our little circle. Range. -5, negative what? Yep. There we go. So the other ones, yeah, you guys have done domain and range a zillion times on that stuff. So, alrighty, there's some issues in this one. There are some issues. What's the first one?
Negative.
Yeah, we can't leave that there. And that has to be the first thing we take care of. So what do we say about this little bugger right here? What did that negative do? Reflect over the y-axis. What would be next to talk about? Remember, after that, we just follow the order of operations. So what would be next? Yep. Right there. What else do we have to explain? Vertical stretch, factor of 3. Last one, reflect over the x-axis. This one, again, extremely important if we want to actually get this correct. So let me just give you a quick sketch of what's happening here. We're saying originally this is the graph of the square root of x, which would be 0, 0, 1, 1, 4, 2, 9, 3. But we're going to reflect that over the y-axis. Then we're going to translate it right 2 units. Then we're going to stretch that thing by a factor of 3. And again, that means you take your y's and you have to basically multiply them by 3. 2, 3, 4, 5, 6. And then we reflect that over the x-axis. Let's see. Where's my original? And absolutely with that one, if we don't follow those steps in that order, we get a wrong answer. Absolutely, we get a wrong answer. So if you're wondering why, okay, Cedar Home, why aren't we graphing all the originals on these and then the final answer? Because most of you are going to grab a graphing calculator. I'm not going to kid myself about that to graph them. Hopefully not so much when you have your AH and K stuff that you're ready to go through. But that's the way you check these. I mean, that is absolutely the way that you check them. You know, this is what I got by the transformations that I listed. Now I punch it into my calculator. If it doesn't end up here, I did something wrong. You know, it's supposed to end up in that position. Let's see. G of x. Anything weird about that one? No, just parabolic again. So this one has a weirdness, doesn't it? What's the weirdness? Okay, so let's talk about what on earth we're going to do with all of this. First of all, this 5 piece, where can that go? Looking better, but still not our H and K stuff, right? What's keeping it from doing that? Yes. Now, can you do that? Can you divide out a 4? No, not a 4. You could take a square root of 4, because square roots can only be multiplied by other square roots. So what would we have to put for the back term so that if we did multiply this by 4, we'd get back to 2, which is 1/2. Now, don't we know what the square root of 4 is? Yeah, it's 2. Now I know you guys could describe all the transformations there, because this would be in the right order. So we'd say we got to go 1/2 to the left, then we've got a vertical stretch factor of 6 and a reflection over the x-axis, and then we're going to go up 5. And there it is. All right. Just a couple minutes to spare. Okay. Well, that's good. You know, we talked about all the ones that I knew were going to have some weird stuff. And sometimes that, you know, drawing all those transformations can be kind of a pain. You can thank Mrs. Peterson for this. So she said, you know what, just to help you out, I'm going to go ahead and make the original graph on here so you can do all of your transformations right on